the last lecture we had seen the concept of moment, and when we were talking about the moment, we have said that, say, to some link which is given in, say, this manner, whose one end is hinged and some force is applied which makes an angle alpha with horizontal. The length of the string, length of this particular link is given to us as, say, L, and that link is making an angle of theta. Suppose I name this as AB. Then we had seen that the moment of force F, moment of force F about point A, denoted as MA, will be equal to F into perpendicular distance. So it is going to be F into perpendicular distance, and we are required to drop perpendicular on the line of action of this particular force. So we will be dropping perpendicular on to this line of action of force, and if this distance is known to us, let us call this point as P, then it is going to be F into AP. But finding moment in this manner will be a difficult task, because we are required to find the distance AP as such. Instead of that, we can go for finding the components of force F and then try to find the moment. Of course, when we talk about the moment, I am going to consider it as clockwise positive, and this moment is going to be the clockwise one. So I can proceed further and try to redraw the figure. Now this is link AB, which makes an angle of theta with horizontal, and this was force F, which makes angle alpha with horizontal, and this distance is L. Now we can find out the components of this force in the vertical direction as well as in the horizontal direction, and they will come out to be F cos alpha and F sin alpha. And when we want to take the moment about A, then as force F has been put in the component form, we will be talking about the components of this force only and not force F. And a vertical force into the horizontal distance, if I call this distance as, say, R1, will be the moment of the vertical force F sin alpha about A. And similarly, the horizontal force, which is F cos alpha, into the vertical distance, which I can call it as R2, will give me moment of F cos alpha. And so moment about A will be vertical force F sin alpha into horizontal distance R1, and the horizontal force F cos alpha into the vertical distance R2. Now we can check that the direction of the moment F sin alpha is going to produce a clockwise moment, and so is F cos alpha. So both of them are positive. Our consideration is again the same one, clockwise positive. Now R1 and R2, they can be determined because we know the length L and the angle subtended by this length as theta. So R1 will be L cos theta and R2 is going to be L sin theta. And so it can be written as F sin alpha into L cos theta plus F cos alpha into L sin theta, and which gives me the answer as F into L into sin of alpha plus theta. We are not going to remember this as a formula, but just remember that the moment can be found out easily if we divide the force in the components. A numerical problem can be always solved. So we can say that find moment of force F equal to 100 newtons about point A when theta is 60 degrees and alpha is 15 degrees. So a numerical problem can be always solved. Now the question may arise even in the exam related to the same problem. As the link is making 60 degrees, the question could be find horizontal force to be applied at point B to produce same moment. This could be the first question. Second question could be find vertical force at B to produce same moment, and the third question could be find smallest force to be applied at B to produce the same moment. Now this is altogether a conceptual question, we can say. We have already got the answer in the first case, which is moment about point A of the previous problem. This problem continues with the previous one. Let us consider the horizontal force to be applied at B. We will have to solve it. Here some force F is to be applied, and as I start with the first case, I can draw a figure. This is length L, A, B. This angle is theta, and we are required to apply horizontal force at B to produce the same moment. Let us call it as F1. The second problem, it says that you are required to apply a vertical force at B to produce the same moment. Let us call this force as F2. And in the third case, we are not given the direction of the force, but still we are required to find the force which is the smallest force to produce the same moment about A. So we cannot show the direction. Now first problem can be very easily solved because the force is horizontal. The moment will be taken by considering the vertical distance, and therefore we can say that moment about A of this force F1 will come out to be F1 into the vertical distance, which is L sine theta. And we already have this to be equal to moment about A of that force F, which we have already calculated, or we can simply equate the previous answer. We can say that moment of F1 about A is F1 into L sine theta, but F into L into sine of theta plus alpha is equal to F1 into L sine theta, and therefore F1 can be calculated. Exactly in the same manner I can say in the second case, that is F into L into sine of theta plus alpha will come out to be F2 into L cos theta, and therefore F2 can be calculated. In the third case, it is said that we are required to find the smallest force. Now the force can be applied, say, in this manner, horizontally, one case, then the distance is going to be the vertical distance. Now if I apply a force which is in some direction, say like this, then the perpendicular distance will be this one. If I apply the force in any direction, every time I will be getting the distance which is going to be smaller than length AB, that is L. Now we have a formula, moment is equal to force into perpendicular distance, and you will find that if I apply the force in any direction, the distance that we are getting is always smaller than length AB, and that is also pretty obvious because you will be taking L cos or L sin that will come into picture, and you will not be getting the length L. So the perpendicular distance will be maximum and its value could be L. So we are going to give a consideration that if the force is to be minimum, if we want to have the minimum force, and if the product is going to be the same one, then the distance should be the maximum one, and the perpendicular distance can be maximum, which will be L. And if perpendicular distance is this length AB, then the force that is to be applied should be perpendicular to length AB or link AB, and so we can have force F3 which is drawn just perpendicular. That means if this angle is theta, then we can very well calculate how much this angle will be, because it is respective perpendiculars. But we don't have to find even that angle, we can specify that angle later, because now this is perpendicular, this is horizontal, so the angle made by this with horizontal is going to be theta. This is 90 degrees, so obviously this angle will come out to be 90 minus theta. The formula which contains this particular sine term, that sine term should be considered as the maximum one. Ultimately we find that force F3, which is going to be the minimum force, and its direction is perpendicular to link AB, and therefore F3 can also be calculated, because we now get the formula as F3 into L is equal to F into L into sine of theta plus alpha, and therefore F3 can be calculated. Therefore F3 can be calculated some value, and this F3 is going to make an angle of 90 minus theta with horizontal, and theta was given to us 60 degrees, so F3 should make an angle of 30 degrees with horizontal. One of the very simple straightforward concept that we are going through, finding the moment, the force which is not passing through the given point, and because of the offset there will be some rotation. In all these cases link AB is going to rotate about point A. So in all these cases the resultant moment is clockwise. Problem statement was, given the link at an angle theta and the force making angle alpha, we are required to find the moment of this particular force F about point A, which we have calculated over here with the formula, and it was force that was converted into components, horizontal component into vertical distance, horizontal component of the force into vertical distance, vertical component of the force into horizontal distance. Again observe that though F sin alpha was downward, I did not consider the sign of it, because we are going to consider clockwise moment as positive. We should be considering the absolute forces. We got some answer. There was a numerical associated with it, with F equal to 100 newtons, theta as 60 degrees and alpha at 15 degrees. So just a substitution problem, we can get the answer. Of course, in the exam you are required to write this or derive this formula and then put the values. The second part of the problem was to replace that force by some other forces. Sometimes it is horizontal force, sometimes it is a vertical force, then the smallest force and whatnot. Horizontal and vertical forces, they can be easily solved because only the distance will change. Smallest force at B will indicate that the distance, that is moment, says that the very first problem related to moments. Now let us consider a problem where we are given some beam which will be acted upon by some point load as such. Beam is the horizontal member which will be having supports as is shown over here. It is supported at one end, and at the other end the support is shown in slightly different manner. And we are given some force which is, say, at the center, acting downward, force F. So this is A, B, then the lengths are given to us. This length is L, this is L by 2. And the question is to find reactions at support. Now before we start with the solution, we are required to first of all understand the types of the support. What we will be showing symbolically, its symbol we can say, name, and then the reactions that it can produce. The first symbol is either like this, or sometimes it is shown like this. It is called as the hinge support, and the reactions which will be produced are horizontal and vertical reactions. So you have a vertical force, horizontal force. In general, their resultant could be in any direction. Now let us understand the concept of hinge. Hinge is a support where we might have a support which is, say, welded or hinged to some other plate, which has got say some circular hole into it, and the beam, its end will be circular one and will be passing through this hole. Will be passing through this hole. In that case, the figure will appear like this. Now we also know that this particular shaft or the beam can be rotated. It can be rotated. But if we try to lift it up, it is not possible. If you try to lift it up, obviously the hinge will produce the downward reaction. Or if you try to push it down, then also the upward reaction will be produced. Same is the case with the horizontal. It will produce the horizontal reaction also. So it is not possible that if you consider this as say y-axis and this as x-axis, this cannot be moved in any direction. Of course, if you consider the z direction, it can be moved in or out. But of course that will not be our consideration right now. We want to say that this particular shaft, it cannot be lifted up, lifted down or pulled in any other direction except this z direction. Now this support is called as the hinge support. In other words, if I apply some moment to it, like this one, then the shaft can rotate. Another consideration, the hinge can be shown in this way. There is a beam or link, say which is like this, which has got a hole into it, and the support is like this, the same part. And I am going to fix up some rivet or some key through this to restrict the movement. Now this particular beam, it can be rotated. Pictorially it can be shown in this manner. And there is a part behind also. There could be some restriction over here on the other side. And then some common circular part is given into it. So this can be rotated, but it cannot be pulled up or down. A support reaction which is called as the hinge. Here the rotation is possible. This link can take another position like this, possible. It can be in this direction, possible. But if you try to lift it up or down, it is not possible. It can have only the rotation in any manner. That means the hinge support cannot restrict the rotation. Like over here it was along Z. Similarly over here, if I consider this as horizontal direction and this as vertical direction, then you cannot move it horizontally or vertically. It cannot be moved, the link cannot be moved in this manner, or it cannot be pulled up, but it can be rotated. This end is going to remain fixed one, but it cannot prevent the rotation. So the reaction cannot have the moment part into it. It cannot support the moment, but it can support the horizontal as well as vertical forces. This is the first type that we have, called as the hinge support. The second one, which is shown pictorially as this one, or sometimes it is shown even in this manner. Or even there are cases when it is simply shown like this, and the beam will be resting on it. Here the beam could be going like this. Beam could be going like this, called as the roller support. And roller support will always give the reaction perpendicular to the surface on which it is resting. I am not saying horizontal or vertical, because if the roller is placed, say, on the inclined plane, if the roller is placed on the inclined plane supporting some beam, then the reaction that will be produced will be perpendicular to the surface on which the rollers are resting. And remember that this is simply the roller, there is no perfect contact as in case of hinge. It is not simply resting on it. In case of hinge, it is even locked. In case of rollers, it is not locked. So if I try to pull this up, then these rollers are likely to get lifted. They are simply resting on the particular surface. And so, like in this case of chalk, if I try to push it down, it will give me the reaction. But if I try to lift it, it can be very well lifted. That kind of contact is there. And so it will be the reaction which will be simply perpendicular to the surface and can take up the downward load, that is the load towards the surface. Second type of support, roller. The third type of support is generally shown in this manner. Which is called as the fixed support, and it can take the vertical reaction, horizontal reaction, as well as it is going to restrict the movement. It is as if some nail is put into the wall. So it is put into the wall. There is some part which is inside. Now if I try to attach something to it, say some bag, it can very well support that. If I try to put some string to this and pull it in this direction, it can even support that. And even the movement in this direction can be very well supported, because it is not going to rotate in any direction. Such a support is called as the fixed support. It is capable of providing the reactions in horizontal vertical direction, that is in any direction in that particular plane, and it can even support the movement. So these are the three types of reactions which we will be dealing with, and these reactions will be required while solving the problem, because we are required to show the directions based on the type of the support. I would be always suggesting that instead of dealing with the given figure with these symbols, let us redraw this figure, because the reactions happen to be the external forces, and even the applied forces are the ones which are external forces as such. Like in this case, force F is external to that particular beam, whose reactions are to be found out. We will be even showing the reactions, replacing those symbols by the corresponding forces, and so another figure should be drawn just below it. Where I will show this beam AB by a straight line, force F which is already there. At A there is hinge, so I will assume vertical reaction at A as VA and horizontal reaction at A, replacing the hinge by the reactions. And at B there will be only vertical reaction, VB, because it is a roller support. The question is, why I have taken these forces upward and why HA towards right? Of course, there is no answer to this problem. You can actually take these directions in whatever manner you want, and the final answer will correct the direction if you have made some mistake into it. Now in this case, we have got unknowns as HA, VA and VB, and to find them, because it is in equilibrium, it is stationary, which is of course indicating that it is in equilibrium. External forces, they are in equilibrium. Then our standard equations like sigma fx equal to 0, sigma fy equal to 0 can be applied. So if I apply sigma fx equal to 0, I find that there is only one force which is horizontal, HA, towards right, so positive, equal to 0. There is no other force. So I get solution to one of the unknowns, HA. Now if I write the second equation, sigma fy equal to 0, left to right I am going, VA upward assumed positive, F downward negative, and VB assumed upward positive equal to 0. And so we get VA plus VB is equal to 0. Now there were three unknowns, and in equilibrium we had studied up till now only two equations. We have studied only two equations, and there are three unknowns, VA, VB and HA. HA we have found out, and we have got the equation VA plus VB equal to F. Now to find any of these unknowns, VA and VB, we are required to have one more equation. As this beam is stationary and it is not even going to rotate in any direction, we will go for the third equation called as sigma moments are also balanced, and say sigma moment about A is also 0. This is the new equation, equilibrium for the rotation. Now if I am to take moment, I will have to say first of all which direction I am considering it as positive. So I am considering clockwise direction as positive one. If I am to take moment about point A, then VA and HA are passing through it, and so the perpendicular distance of any of these forces from point A will come out to be 0. If at all we are required to write it, we will write it as HA into 0 because it passes through A, plus VA into 0 because it passes through A. And if it is force F which is to be considered, then force F is vertical, so the perpendicular distance will be the horizontal one, which is L by 2 given to us, and the moment of force F is going to be clockwise about point A, and therefore we can write it is F into L by 2 clockwise, so positive. The remaining force is VB, which is acting upward. Perpendicular distance from A is L, and so it will be VB into L, and if you see the sense of rotation, it is anti-clockwise, so it will be minus VB into L is equal to 0, and therefore we will get VB is equal to F by 2. So we get the solution. Substituting in the previous equation, we have the equation VA plus VB is equal to F, and so it will be VA plus F by 2 is equal to F, and therefore VA will also come out to be F by 2. And then we are required to write the final solution again in the diagram form. This was force F acting downward, A, B, reaction at A is F by 2, vertical, there is no horizontal force. Reaction at B is also F by 2, vertically upward. Observe that the force got supported by two reactions which are equal and opposite in direction because of the symmetry of this particular figure. Because of the symmetry of this particular figure, the forces that we got, the reactions that we got at A and B, they were having the magnitude as half the given force. So symmetry of the problem will always play some role, but it need not be always the assumption that will go along with it. Let us consider what will happen if force F, instead of acting at the center, is acting at a distance L by 3. So I am making the change in the position of force F. It is at a distance L by 3. It is at a distance L by 3 from the support. Then if we are required to find the reactions, the procedure is going to be the same. We will have to first of all redraw this figure. We have shown the reactions as HA, VA and VB. We get sigma Fx equal to 0, so HA will be 0. We also have sigma Fy equal to 0, so VA minus F plus VB equal to 0. Even this equation remains the same. And when we go for moment, there will be a change into it. There will be no moment of HA and VA. It is force F into perpendicular distance. Perpendicular distance this time is L by 3. And therefore, when we calculate VB, it will come out to be F by 3. If you substitute into sigma moment equation, then L will cancel and VB will be equal to F by 3. If I substitute VB equal to F by 3 in our sigma Fy equal to 0, we will find that the reaction at A will come out to be 2F by 3. And ultimately the answer will be written as force F, reaction at A will be 2F by 3 and reaction at B is F by 3. Some conclusion is to be drawn over here. As the force is moving towards point A will have to take up the most of the load, the most of the reaction will be given by A, and reaction given by B will reduce as the force moves away from B. Of course, this consideration will be useful to check overall loading and where the reaction should be more. But this is so far as only one force is acting onto it. What will happen if there are multiple forces acting at the same beam? Say there is one more force. So this was F1, say, and this is F2, which is acting again at a distance equal to L by 3. And so the figure will get modified. It will be F1, F2. So two forces are acting. Due to equilibrium, sigma Fx is 0, so we will get HA to be equal to 0. Sigma Fy equation is to be rewritten now because there is one more force which is coming into picture. So it will be VA minus F1 minus F2, both the forces are acting downward, plus VB equal to 0, and so we get VA plus VB is equal to F1 plus F2. As we proceed to take the moment about point A, we will find that moment of F1 is F1 into L by 3, which is a perpendicular horizontal distance. F2, the distance will be 2L by 3 and is also clockwise, so positive, whereas it will be minus VB into L equal to 0. So VB can be calculated. VB comes out to be F1 by 3 plus 2F2 this VB can be substituted. We have the equation as VA plus VB as F1 plus F2, and when we substitute VB, it will be VA plus F1 by 3 plus 2F2 by 3 equal to F1 plus F2, and so VA will come out to be 2F1 by 3 plus F2 by 3. And so the final answer as we represent it in the diagram form, we will have two forces, F1 and F2. VA is 2F1 by 3 plus F2 by 3, whereas VB will be F1 by 3 plus 2 F2 by 3. Again the same consideration, as F1 force is nearer to A, most of the F1 load is taken up by A, and point B will be sharing the less load. But F2 force is nearer to B, so B is taking the most of the load, whereas A is taking the smaller part of it. And so the overall reaction is going to be the combination of individual reactions, we can say. Here if only F2 is present, the reaction will be F2 by 3 and 2F2 by 3. If only F1 is present, it is 2F1 by 3 and F1 by 3. Both are present, there will be addition of the reactions. And if F1 is equal to F2, say F in each case, then reaction at A will be 2F by 3 plus F by 3, that is F, and again F by 3 plus 2F by 3, it will be F, and you will find that again symmetry has worked out. The net downward load was F plus F, that is 2F. Each reaction will be F in this case because of the symmetry. So a single load, the reaction can be found out. Multiple loads, we can find out the reaction. But up till now what we have dealt with were all vertical forces. Now let us consider that force F1 is making some angle, say theta 1 with horizontal, and force F2 is also making some other angle, say theta 2 with horizontal. Now as we redraw the figure, we will have to simply show those angles. Need not measure the actual angles, this is just the representation that we have. We are replacing the supports by the forces here, and that's why the figure should be redrawn. F2 at an angle theta 2. Now as we proceed further, actually we will have to go for one more diagram, initial cases, and afterwards we will be through with actually drawing the diagram, or without drawing the diagram writing the equations. I can have this VAHA as they are. Force F1 can be divided into components. There will be a vertical component of it. If I complete this triangle, this is opposite side of theta 1. So the vertical force will be downward, which is F sin theta 1, and horizontal force is towards right, which is F cos theta 1, F1 cos theta 1. Similarly for F2, the net downward force will be F2 sin theta 2, and the horizontal force is towards left, it will be F2 cos theta 2, and the reaction at B is only vertical reaction, VB. Now the three equations. There are still three unknowns, VA, HA and VB. So when I write the first equation as sigma Fx is equal to 0, it will be HA towards right positive plus component of F1, which is F1 cos theta 1 towards right, so positive, and component of second force F2, which is F2 cos theta 2 towards left, so negative, is equal to 0. And we will get HA as F2 cos theta 2 minus F1 cos theta 1. So we have got the value. Now of course here, if F1 cos theta 1 happens to be greater than F2 cos theta 2, observe the figure that if this horizontal force over here is more than F2 cos theta 2, resultantly this force will be more than this, effectively the beam will be pulled towards right and the reaction should be towards left. So our assumed direction will be wrong. So I repeat, if F1 cos theta 1 is greater than F2 cos theta 2, in that case there is a net force acting towards right, HA should come out to be negative. If you observe, it is F2 cos theta 2 minus F1 cos theta 1. If F1 cos theta 1 is greater than F2 cos theta 2, HA will turn out to be negative. That negative value that you are getting over here will simply force us to change the direction of that force HA, which was assumed to be towards right. In the final answer, we should be writing it as towards left if HA comes out to be negative. Let us consider to the second part, that is sigma Fy equal to 0. The equation will be written as VA minus F1 sin theta 1 minus F2 sin theta 2 plus VB is equal to 0, and therefore VA plus VB will come out to be F1 sin theta 1 plus F2 sin theta 2. And then sigma moment about A. Up till now I have been taking the moment about A. Actually it could be any point on this particular beam about which you can take the moment. The criteria for choosing the point at which we want to take the moment, from our calculation point of view, we will say that it should be the point at which the maximum unknowns are intersecting each other, like HA and VA and VB. Out of that, VA and VB are not intersecting. So HA and VA are passing through a single point A. So we should be passing or taking the moment about point A only. So here I am choosing point A again to take the moment. HA and VA will not have any moment. Similarly, F1 cos theta 1 passes through point A and F2 cos theta 2 also passes through point A. Their moment will not come into picture. There will be moment of F1 sin theta 1. Of course, perpendicular distance is horizontal 1, which is L by 3, clockwise positive, plus again F2 sin theta 2 will produce a clockwise moment, its distance is 2L by 3, and minus VB into L equal to 0. And so we can calculate the value of VB, which will come out to be F1 sin theta 1 upon 3 plus 2F2 sin theta 2 whole thing upon 3. And substituting it in the previous equation, I can find VA, which will come out to be 2F1 sin theta 1 by 3 plus F2 sin theta 2 by 3. And then the final figure should be drawn and the reactions should be shown. Again, the vertical forces, they are shared by VA and VB, and HA has taken the entire responsibility to balance the horizontal components of these two forces. So actually, removing F1 cos theta 1 and F2 cos theta 2, the problem will reduce to the previous case. Vertical forces will be balanced by the vertical reactions, horizontal forces will be balanced by the horizontal forces or horizontal reactions. Now at point A, actually, if we are required to find reaction at A, then we will have to use the same technique. We are required to square and add the horizontal and vertical reactions, and then even the angle made by that reaction can be calculated. It is going to be tan inverse of VA upon HA. And then the final reaction at A can be shown in the magnitude and angle format. Even answer in terms of HA and VA is also a valid answer. Some application problem. It is given that some crane is lifting the weight of 200 kg. Support A is the hinge support, support B is the roller support, and the weight of that particular crane is given to be, which is not shown in the figure, it was given to be 2400 kg. Its location of center of gravity is given to us. We are required to find support reactions. We are required to find the support reactions. Now if this figure is to be redrawn, of course we will have to draw it, say, in this manner. No need to show any internal details as such. And the weight which is to be lifted, so this should be converted to newtons by multiplying it by 9.81, and even the weight of the crane to be converted to newtons. This was point G, this is C. At point A there is a hinge, so there will be horizontal reaction HA as well as vertical reaction VA. At point B there will be a reaction which is perpendicular to the support, and so in this case it will turn out to be HB only. It is perpendicular to the support, the surface on which it is resting. Now if we consider the first equation as sigma Fx is equal to 0, we will get it as HA plus HB, both are towards right, equal to 0, and there is no other horizontal force. Both the weights are acting in the downward direction. When we consider sigma Fy equal to 0, then VA is acting upwards, positive, minus 2400 into 9.81 minus 2000 into 9.81 equal to 0, and so you will get VA to be equal to 4400 into 9.81 newtons. The third equation is sigma moment. There are three unknowns. I will be again taking moment about point A. So sigma moment about A equal to 0. Now observe that when we take moment about point A, due to weight there will be a clockwise moment, vertical force into horizontal distance given to us as 1.5 meters. Then the weight which is to be lifted, 2000, that is also going to produce a clockwise moment, and it will be 2000 into 9.81 into perpendicular distance, which is 4 plus 1.5, 5.5 meters. And finally HB is also going to produce a moment, but it will be producing anti-clockwise moment, and it will be HB into perpendicular distance, that is 2 meters. So when we write the equation, it will be 2400 into 9.81 into 1.5 clockwise positive weight of the crane, 2000 into 9.81 into 5.5 clockwise positive, and minus HB into 2 is equal to 0, and therefore we will get the answer for HB, so many newtons. Once we get this HB, it can be substituted and you will get HA to be equal to minus HB. This answer is bound to be the negative one, newtons. Now when I am saying that HA will turn out to be negative, it is, you will have to understand the effect of these two loads. If you consider point A, you will find that due to these forces, this point A will try to move towards right, because it is the moment which is given in this manner. It is going to rotate in this manner, so A point will sense a force which is pulling force towards right, and so the reaction at A should be negative. Whereas on B, that is, this entire rotation load will come into picture, so roller will be pushed inside the particular wall, and so wall will be giving the reaction which is outward. So this direction will come out to be the correct one. HA will turn out to be negative as we are getting it over here, and so the final answer will have HA towards left. So HA will be towards left and VA is upward. And so when we try to find out the reaction at point A, it will be HA towards left, VA upward. And so if you try to simply complete the parallelogram, you will find that this is the net reaction at point A, RA, and its angle also can be calculated. So the problems are using simply the three equations, sigma fx equal to 0, sigma fy equal to 0, as well as sigma moment equal to 0. Only thing is you will have to give some consideration while writing these equations and taking the moment. The problem is to be solved in a straightforward manner. Even if the figure changes from horizontal to vertical, as long as you take the reaction directions correctly, rather the reaction positions correctly, even if the directions are wrong, the care will be taken by the solution. When it gives some negative answers, final answer should contain the correct direction. The assumed direction may turn out to be wrong, but it will be corrected by the numerical answer that you will be getting. Also, if the loads are given in kilograms, you are required to convert them to newtons, which is a standard practice. The forces are to be written only in terms of newtons. So the further problems which we are going to solve in this case, they will be all related to finding the reactions where the forces are not the concurrent forces. These forces which are acting on the particular body are not the concurrent forces. They are having some offset. Sigma fx, sigma fy will be still valid, but the sigma moment is the additional equation which will come into picture, and the moment can be taken at any position.